Okay, work energy theorem is, in my opinion, the most important concept in high school physics. Okay, it tells us how objects get their energy, how they do work, okay, how they move around, okay, things like that. It is the basis for basically all physics. Nothing can happen if there's no what? There's no energy, okay? And the work energy theorem tells us the relationship between work and energy. If you have no energy, can you do any work? Like, you know, mom and dad come in, it snowed like 1.5 feet, and you're like, hey, go out and shovel the driveway. And you say, I have no energy for that. I mean, you're lying, but okay. If you actually had no energy, would you be able to shovel the driveway? No, because you'd be dead. Okay, that would be bad. We wouldn't want that. Okay, but I mean, if you don't have any energy, then you don't have any ability to do work, because when you're doing work, you're using energy, right? Or more accurately, you are transferring energy to something else. Okay, a very simple example of doing work would be if this hole punch is just sitting here on the table and I pick it up and raise it up above the table a little bit higher. Okay, in that case, I've done work, because now the hole punch has more what? It has more potential energy, right? Okay, when it was sitting on the table, did it have potential energy? Yeah, it could still fall to the floor, right? It's still above the floor, right? So it had some potential energy. If I pick it up and put it higher above the table, it's now also higher above the floor. It has more energy. I would much rather, if it was going to fall on my foot, that it did it from this height than this height, because at this height it has more energy. And energy is the ability to do work. Okay, so work is a transfer of energy, and energy is the ability to do work. You can't have one without the other, right? It's chicken and the egg. Of course, all scientists know the egg came first, because chickens are birds. Birds evolved from reptiles, and reptiles lay eggs. So the answer to that question is the egg came first. It is not a philosophical question in any way. Science has unequivocally answered which came first, the chicken or the egg. It is the egg. Doesn't matter. They asked which came first, the chicken or the egg. Eggs came first because chickens evolved from reptiles. Okay? They didn't ask where the egg came from. They just asked which came first, the chicken or the egg. I'm telling you, the egg. Okay?
So we say that potential energy is when something is like above ground, gravitational.
That's gravitational, yes.
Yes. So what do you classify as like the base of all, like the ground? Like
ground level, exactly.
It's higher than sea level.
It is. It's all about your reference point. The most common reference point. It's all relative. Yeah, exactly is the answer. Yeah. Okay. Our most common reference point is ground level, because that's, I mean, I can't drop something to sea level from here, right? But if I was in an airplane, they usually have an altimeter that doesn't measure ground, that doesn't measure sea level. It measures ground level, right? Because having an altimeter and landing at Calgary International Airport, and that altimeter staying about how far above sea level, is going to lead to disaster, okay? Because you'll be plowing into the ground at a high rate of speed, yeah, even though the altimeter says you're still about 1,100 meters above sea level, okay? So potential energy is, well, at least gravitational potential energy, is possessed by any object that's above ground level, because it can fall. If it falls, what does that potential energy turn into? It turns into kinetic. Okay, so that's kind of the simplistic view of it. Okay, work energy theorem looks at when I do work, I change the energy of something. So when I changed the energy of the hole punch, it was because I used energy to do it. Okay, however much work I did is how much energy was gained by the hole punch. Everyone all right with that? And that's, again, in the perfect physical world where no energy is lost to friction and sound and heat and other things. Okay. No, the air doesn't have, we would assume the air, at least simplistically, has no energy. But as I drop this, I can hear it falling, right? I hear the air rushing out of the way. Well, sound is a form of energy. That's where some of the energy is lost to air resistance. So if I lose energy to air resistance, it becomes other forms of energy. I don't truly lose it. It's just not doing what I want it to do anymore, right? So it would be heat, sound, things like that. Okay, so if this hole punch fell on my foot, okay, it would hurt, right? Would it do work on my foot? Is it really changing the energy of my foot though? No. Well, in this case, it's changing the energy from one form to another. My foot's not really gaining energy, but work is also a change in shape sometimes. I think we could agree my foot would probably change shape in an undesirable way. Okay. Now, the energy, okay, possessed by the hole punch would turn into other forms of energy. All right. There would be the sound of breaking bones. Okay. The sound of clanging on the floor, right? All of that kind of stuff. There'd be some heat and things like that. So all that energy is still conserved. It's just not making the energy of my foot increase. Okay. It's just damaging my foot and changing its shape.
Have scientists figured out a way to calculate changes in energy in things that are non-scientific world?
Yes, absolutely.
So like
We do it in physics 20.
So like if I like the heat say drops, they calculate how much power.
Yep. Yeah, all you do, and it's actually quite simple. Okay, what we do in what it's a terrible color to use. Okay, work is essentially a change in energy. Okay, in a perfect physical world, wow, I can't find a good color here. Okay, in the perfect physical world, the energy before and the energy after are equal. Okay, in the real world, that never happens. Okay, so what we say is that work is the change in energy. So work would be EF minus EI. Okay, that's what delta means, right? It's final minus initial. So I could calculate how much energy the hole punch had before I dropped it. And I could probably calculate how much kinetic energy it had when it hit my foot. By subtracting those two numbers, I know how much energy is lost to the other forces. Okay, and with better formulas and more knowledge, I'd be able to calculate exactly how much became sound and how much became heat and all that. Yeah? Okay. All right, so we're going to work a little bit with that stuff, but we won't do this work against non-conserved forces thing until physics 20. Okay, so the big thing is that the work energy theorem is this formula here. Work is a change in energy. Okay, delta means final minus initial. Okay, so put simply, work is the final energy minus the initial energy. That could be potential, it could be kinetic, it could be mechanical, which is the sum total of both of them. Okay, in Science 10, we only deal with one or the other. Okay, work will either be a change in potential or a change in kinetic. We get to Physics 20, we'll deal with changes in mechanical or both at the same time. Okay, there's another way to calculate work, right? Because when I do work, I have to exert a force in order to make something move. Agreed? Okay, and I actually do have to make something move in order for me to change its energy. So work can also be calculated this way. Okay, that formula is also on your formula sheet. Work is force times distance. I'm pretty sure it's in there at some point, but it's on your formula sheet as well. Okay. So the more force I exert, the more work I should do. Is that what that formula says? If I exert more force, I should do more work, provided the object moves. If the object doesn't move, then I'm not doing any work. Okay, at least not on the object, because the object's energy isn't changing. Okay, so when I exert a force over a distance, the object has to change its energy. If distance is 0, then the work is 0. Okay, there's no way for me to change the object's energy, at least its mechanical energy, okay, if it doesn't move.
You end up like a bowl that you couldn't push, and you kept on trying to push it. You would still get tired even though it's not moving. Where do you do that?
Newton's third law. If I push on this wall, okay, the wall's not going anywhere. I'm not doing any work on the wall. But you're right, I'm going to get tired. Because what's the wall do when I push on it? It pushes back. Okay, yep. Every action is an equal and opposite reaction. If the wall doesn't push back, I go through. Right? So the wall pushes back with an equal but oppositely directed force. Now, in order to not move myself, okay, I'm braced. And what happens when you exert a force with your muscles? What do your muscles do? They burn energy, but they burn energy because they change shape. And a change in shape counts as work. They shorten. Well, if they shorten, that's the distance over which the force is acting. So I have a force, I have a distance, and as a result, energy is being used by me. It's not doing any mechanical work, but it's being converted into heat and things like that, right? So I'm metabolizing. Yes, I'm going to get tired, but it's not because I'm giving the wall energy. It's because I'm giving the surroundings energy. Okay, like I would, heat would bleed away from me, and that would be lost that way. Yeah, that's why isometric exercises work. Okay? Isometric exercises are ones where you don't change the energy of the weights, you just hold them, right? You don't go anywhere. Isometric means not changing shape. Yeah. All right, is that making some sense? Okay, so the relationship between force and work is that if force goes up, work goes up, okay? As long as there's a distance, as long as distance isn't zero, okay? So that's what kind of relationship then? It's linear. When one goes up, the other goes up. If I double the force, will the work double? Yeah, I mean, assuming distance stays the same, yes, it would double. All right, that's kind of how that works. So it's a linear relationship. The more force you use, the more work you can do. All right. So energy, just like motion, okay, is a measurable quantity. We had trouble measuring it initially because it wasn't something you could actually like fill a cup with, okay, or measure with a ruler, right? But we can measure it and let's say calculate it by measuring other things to an extent. All right, so specifically, energy is a measure of an object or system's capacity to do work. Okay, that's what energy is. If you have energy, you can do work. Okay, and then work is the transfer of energy from one object or system to another. So if you've ever played pool, okay, when one ball hits another, it does work. It transfers energy from one ball to the other. If you've ever seen one of those Newton's cradle things, right, where it's like the 4 balls and they're on the little like strings, and you pull one away and it goes tick 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 and swings back and forth. Okay, that's a transfer of energy, right? When you lift the one ball away, you're doing work. Okay, you've given the system energy. When you let go of it, it falls. That potential energy becomes kinetic. It hits the other ball. That energy is passed through the system to the ball on the other side, which swings up. Okay, its kinetic energy becomes kinetic, comes back down, and just keeps ticking back and forth. Now, does it go forever? No, because you're constantly losing energy. Every time you hear the tick, 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 okay, energy is being lost. There's some sound, there's some heat, okay? It's not a perfectly elastic and perfectly energy conserving system. There really isn't anything like an isolated system, which you learned about the first day, right? Okay, the different systems there. There was open, closed, and isolated. To have a Newton's cradle that went continuously, it would have to produce no sound. There would have to be no deformation of the ball when it hits the others, and there is, okay? No friction on the pivot, swinging points, and all that kind of stuff. Then it would go forever, right? But obviously that's impossible.
The question is like, when the last ball is going up, swing back, will you lose?
No, it's not going to lose energy to gravity. Gravity is what essentially makes potential energy possible. Right? So your kinetic energy is turning back into potential. You're doing work against gravity, but you're not losing any energy. Well, you're losing kinetic energy to gravity. It's becoming potential, right? But gravity is not a non-conservative force. Friction or air resistance is. Okay? We could hear the ball hissing through the air and things like that.
There was no deformity on the shape of the ball. How smooth the plane needs to be for there to be no energy loss.
Oh, I don't mean that it's smooth. I mean that like there would be no mark on the ball. If you have a Newton's cradle and it's gone a few times, like you can see that there's little scratches and marks on the balls where they hit each other, right? So that counts as a deformation. Like some small amount of matter comes off every time they hit. Yeah. Okay. Yes. In space, once an object is moving, provided there's no gravitational bodies around, it would continue on forever. Okay, but you've already done the work, right? Something has already put it into motion, right? So then, yes, according to Newton's first law, It would continue on at a constant velocity until an unbalanced force acted on it. In space, you know, there can be large distances where there are no unbalanced forces. That's not entirely true. There's always some small amount of gravity or stray gases or whatever, right? But like if you were working at NASA and you were part of the New Horizons team, right? Like New Horizons is way out in the Kuiper Belt and there's not much out there, right? But there's still anomalies, gravity that pulls it away. The sun's gravity still pulls on it. Those are all small. But when you're talking about the large distances it has to travel, even a change of a half a degree can mean you miss a planet by a long way, right?
So you're saying like if billions of years ago something exploded and sent rock flying kilometers a second, it's still going that fast right now?
Provided no other gravitational forces have acted on it, yes. Okay. Just recently, NASA's been tracking the asteroid that's gone through our solar system from another. It's our first interstellar visitor that we've discovered. And it was actually a Canadian astronomer that discovered it. But it's this oddly shaped asteroid that's kind of swinging through our solar system. And yeah, it's been traveling through space for a very long time. Okay, and it's now being acted upon by the sun's gravity, and its path is going to change abruptly. Like the sun is here. Most of the planets lie in this plane, right, except for Pluto, which is kind of outside the plane a little bit. Okay, this thing is coming in on a trajectory like this. So it's obviously not from our solar system, okay? And it's going to swing past, not that close to the sun, this is not the scale, okay? But the sun's going to change it because it'll be an unbalanced force and it'll send it swinging on out of our solar system and on to its next. It's actually going to go in and out of our solar system fairly quickly, through the inner solar system anyway. It'd be gone, and I think they said it was going to be a matter of months, be gone. Okay, that's fast. Yeah. Okay. All right, they're saying their opportunity to observe it is very small because it's very dark and it's very small and it's moving quickly, right? So it's hard to track an object like that. All right, so prime example here of work and energy is a mousetrap. Sorry, Jake.
So one of the laws of thermodynamics is energy cannot be created, right?
That's right.
Which is why you can't make a potential motion.
Right.
Why don't they use the energy that is lost when motion, like for instance, the sound that is created, whatever, or the friction? Why can't they use that to create energy?
Okay, so the question is, why can't we use energy that's lost in an energy conversion? Why can't we get that back into the system? And the answer to that is that not all forms of energy are created equal. Some forms of energy are more useful than others. Okay, it's hard to harness sound energy to do something useful, right? Because it's fleeting, right? It spreads out very quickly and is gone, so it's hard to capture. Heat is hard to convert back into other useful forms of energy once it's produced as the result of a conversion, right? So in some ways, we're trying to do that. Lots of hybrid vehicles, their brakes will actually have a thermal couple in them, right? I think I talked about that in the podcast that first day. So that's an example of trying to harness some of that lost energy. But the fact of the matter is you have to lose some of that energy in order for you to stop. Yeah, things like that. So yes, there's a lot of energy that's wasted or lost, but it's hard to re-harness it and get it back into the system. Yeah. It's chemical energy. So there's chemical energy stored in the bonds of the chemical. When the reaction happens, that energy is converted from chemical energy into heat, sound, light, whatever the products of the reaction are. Right? So when we burn fuel, right, we're taking chemical energy, we're converting it into heat, and the heat is then being converted to mechanical energy. So there's 3 energy conversions in burning fuel to make a car move. Every time you convert from one form to another, energy is lost to the surroundings in the form of heat and sound and other things. Does that make sense? Okay. All right, so the example of the mousetrap here, okay, if I'm going to set a mousetrap, okay, I have to change the shape of the spring that loads the killing bar. That's what it's called. Okay, so this spring here, okay, when the trap has been triggered, so it's snapped over, okay, it's got a certain shape. If I want to set the trap, then I have to exert a force through a distance that changes the shape of that spring and puts elastic potential energy into the spring. Then I have to very carefully load the trigger or lock the trigger. Okay, so this is the trigger, okay, and this is the trigger bar, okay, this thing here. All right, so I get the killing bar and the spring put over here, okay, and then I lock the trigger bar into the trigger. Okay, so it's just there's just two holes here and here, okay, and you can just lock the trigger bar into the trigger. All right, so now it's loaded. When a mouse steps on this part, okay, it lifts the back and the trigger bar is released, which then allows the energy, elastic potential energy stored in the spring, to accelerate the killing bar back over. Okay, if you've ever dry fired a mousetrap, I mean, you know, it snaps, right? Like it's quite a loud thing and it jumps right off the floor, okay, when you trigger it. So it's got a fair amount of energy stored in that spring. Anyone ever had their finger caught in one? Okay, like if it's your little finger, it can snap the bones in your little finger because what's it designed to do? Snap little bones. Okay, that's what it's designed to do. Okay, it's designed. I know people that are going, oh, Mr. Clear, you're so cruel. This is, I mean, the reason, you know, the whole expression "make a better mousetrap" is because really there isn't much better than this kind of mousetrap. This is quite humane, actually, because when the mouse steps on here, what part of it gets hit by the bar? The neck. Okay, the neck gets snapped. That's it. It's over. Okay, its death is immediate. Right? It's quite a humane thing, right? Because I know a lot of you are kind of giving me that look. Oh, poor mouse. Guys, mice carry the hantavirus. Okay, that's not cool. Okay? If I have to make a choice, me, mouse, yeah, sorry, mouse. Okay, so the fact of the matter is that we're looking at energy conversions here. In order for the mousetrap to do work, I have to put work into it first. I have to change the shape of the spring and load it. Okay, then it can convert that elastic potential energy into kinetic energy, which will then change the shape of the mouse, make sound, okay, and all those other things that a mousetrap does when it works. You put it on before? Yes. Always put the bait on before you trigger it. Yeah.
I tried to spread peanut butter on a loaded mousetrap. Didn't work.
These are lessons that you learn in life. Yeah. You always, yeah. You wouldn't put bait in like a wolf trap, okay, when the teeth are open. You know, oh, I'll put then you're gonna be carrying around the teeth on your arm. Okay, you don't want to do that. So yeah, always put the bait on first. Okay, yeah, and that's much better. Okay, so does that make sense here? The idea of how work and energy go together, right? I can't do work without energy, and work can transfer the energy that I put in.
There's enough energy in the spring and the elastic that it can lift the mousetrap off the ground.
Oh yeah, they'll pop right off the ground. Sometimes they'll pop like a.
How does that work? Like the work was more than the weight of the object?
Not so much, no. It's just that when it snaps over, like the energy hits the floor, and it's almost like a conservation of momentum kind of thing. Momentum and energy is something you do in physics 30, but I don't want to say the energy was reflected off the floor, but it's almost like that. Okay, the energy is essentially conserved by popping it back up. In Science 24, and when I used to teach that, we would build cars that were powered by mousetraps. So you just stick a mousetrap on the back of the car, and you would put it against the wall and trigger the trap, and it would push against the wall and shoot the car forward. Like there's a fair amount of energy in that spring. If you've ever loaded one of those, like, you know, you have to push pretty hard to load that thing. Okay? They're quite strong. All right, so the idea between work and energy, relationship between work and energy makes sense? Can't have one without the other? Okay. Now, tennis ball. Okay, lots of sports, and sports, the science of sport and equipment is based on the work energy theorem. Right? If I want to serve a tennis ball, okay, I throw the tennis ball up in the air and I hit it. All right? Now, I mean, from a very simple perspective, the harder I swing the racket, the faster I should be able to hit the ball. Okay, so if I increase the amount of force that I use, I should be able to do more work. Okay, but the other part of that equation is the distance over which, sorry, I shouldn't have an arrow over the distance over which I exert the force. If I can exert that force over a greater distance, will I also do more work? Okay, that's where technique and equipment can improve the ability of any athlete to do whatever their sport is. Right? Give you an example. Okay, with the tennis racket. Okay. a racket is not a paddle, right? The difference between a racket and a paddle is the face. A paddle is solid, a racket has strings. Everybody with me? What's the advantage of strings versus a paddle? Less air resistance. What else? Strings are elastic. What else? Lighter. Means I can move it faster. Okay. Oh. Doesn't produce as much sound. Yeah. So these are all advantages of a racket over a paddle. Okay. Which is why you don't see very many paddle sports other than cricket. Okay. Ping pong. Yeah. Okay. Ping pong uses a light ball though, right? Okay. You don't see many paddle sports with a heavy ball. So the advantage of the racket and the advantage of technique is if I can increase the distance over which this force is exerted, because the only way for me as an athlete to increase the force is to train and get stronger, right? That's the only way I can do that is to improve that part of me, my strength. Okay. The other way to improve is to improve my technique or get better equipment that can allow me to exert that force I'm able to exert over a greater distance. So with a racket, okay, you can see kind of up in this top part here where the ball is changing direction, okay, because it was thrown straight up in the air, right? There's going to be a time where the ball is actually behind the frame of the racket. So if this is the racket frame, okay, and the strings are on there, the strings will go back and the ball will be sitting back here. Okay? The advantage of that over a paddle is that that's not possible on a paddle. Okay? So the ball sits in the racket for a longer period of time while I'm exerting a force on it, which means I do more work. I can hit that ball harder. Well, not so much harder, but I can make it go faster because I'm in contact with it over a greater distance. No, because if you have too loose of strings, then you'll lose some of the energy because it won't be as elastic of a collision. Okay, you'll deform the string. The deformation of the strings won't be as elastic because they're too loose. Okay, so the ball could move around if they're not tight. Yeah. Oh, it does. I'm saying if you hit it harder, you're going to hit it faster. But the only way to hit it harder is to get stronger. So let's say, you know, I'm already an elite athlete. I've trained my whole life. I can't really make a lot of improvements to my strength anymore, right? Well, then technique and equipment is my next best bet, right, for improving that situation. Okay, hockey sticks are a prime example of this. Back when I was in school, okay, hockey sticks were made out of a chunk of tree. Okay, they were wood, they were heavy. Okay, you didn't have to buy 5 of them in a season generally because they lasted a long time. Okay, what are they made out of now? They're graphite, carbon fiber. Okay, and the advantage of them is they're lighter and flex. They flex like crazy. Okay, so if I'm looking at like a traditional wooden stick, okay, I mean they'll bend a little bit. Wood is a little bit flexible. Okay, but the arc through which a traditional wood stick will flex is very narrow. Okay, whereas a modern carbon fiber stick, okay, it can really bend. All right, if you've ever watched, like sometimes they'll shoot the guy taking a slap shot in like 240 frames per second. Okay, that stick is bent, like out like this, okay, against the ice. Well, look at the distance over which the force can be exerted. Is it a lot greater? And then you also, in addition to that, have the snapping effect of the elastic reaction of the stick. Okay, after that, where you didn't have that nearly as much with a wooden stick. Okay, so technology has allowed hockey players to hit faster shots because now they have better equipment. They can exert their strength, which is considerable if they're a professional hockey player, over a greater distance. Okay, which means faster puck, harder to stop. Okay, that's why goalie equipment kept getting bigger and bigger and bigger. Okay, it's like a what do we call it? Like an arms race. Okay, like, you know, the offense gets better, so the defense has to get better. Yes, the speed would have to do with your power. Okay, so again, that has to do with the strength that you have and whatever. We don't get into power until physics 20, but yes, it does. Okay, because the stronger you are, the faster you can move, generally. I don't understand how the numbering system works, but that seems logical. Okay, there's probably an upper point to where that flex is effective, right? Anything that's elastic has a certain point beyond which it's no longer truly elastic, and its shape is being altered in a non-conservative way. Same thing with a rubber band. Like you can pull a rubber band, it's pretty linear until you get to the point where it really is hard to stretch it anymore, and then you're actually doing damage to the elastic nature of the object. Okay, and that would be true for any flexible object, like a bow and arrow. You don't just pull on the bow as hard as you can and try and pull the ends together. Okay, you want to pull them together a certain amount, but there comes a point where if you pull them too far, it's not an effective bow anymore, right? Okay, same would be true for a stick, which is why sometimes they snap, right? You just get them, if they flex too far, they break.
You can't have like, because we use like a scalar distance speed because you can't have negative work. So it can only be.
Actually, you can have negative work. Yeah, work is scalar, so is energy, but work can be negative. I know that's going to seem weird, okay, but I'm not contradicting myself. When I picked up that hole punch, the work on the hole punch was positive. The work from my perspective was negative because I lost energy, right? I transferred energy from me to the hole punch. So energy is conserved, which is why it's scalar. But from my perspective, it was negative work because I no longer have that energy. Yeah? Does that sort of make sense? Yeah. All right. So does that make sense there, the energy transfer part? Okay. We change any part of this formula, okay, and we've got more work. Okay. Okay, so work is also related to the force that's acting on the object. The greater the force, the more work is done on objects of the same mass. Okay, mass can also affect the amount of work done, as a more massive object would require more energy to move. All right, so if I wanted to get it, let's say, to the same speed or the same height as a light object, right? That's where these two formulas come into play. Okay, these are the formulas for gravitational potential energy and kinetic energy. Okay, gravitational potential energy is the energy you have because you're not sitting on the ground. Kinetic energy is the energy you have if you're moving. Mass is part of both of those for this reason. If I'm only capable of doing 10 joules worth of work, okay, I can lift a small object, let's say a 2 kilogram object, higher than I can lift a 5 kilogram object if I can only do 10 joules of work. Agreed? But those two objects, if I lift them as far as I can in doing 10 joules of work, both have how much energy? 10 joules. Okay? But the one that's heavier isn't as far off the ground. It doesn't need to be, right? Because it's heavier. It has more mass. All right? I mean, you think about it. If someone drops like a bolt from the top of a building that's being built, is that still dangerous to you? Yeah, it's just as dangerous to you as having a piano dropped on you from this far. Okay, they would have the same amount of energy. I mean, in the perfect world where it didn't hit terminal velocity and just continued to accelerate all the way down. Okay, dropping a piano on you from this high or a bolt from 200 meters, they're both equally dangerous to you. Okay, they both have energy. Maybe even the same amount. I don't know. I'm not doing the calculation in my head, but okay, you kind of get the idea. Terminal velocity is where air resistance and gravity, the forces balance, and the object stops accelerating. It's the fastest you can fall through the Earth's atmosphere. Not so much how heavy you are, but how much air resistance you can make. Like if you go like this, you fall like a pencil. You fall faster than if you spread out, right? But yeah, it's not. Yeah. When you're falling through the Earth's atmosphere because of air resistance, there comes a point where you can't fall any faster. Not really. I mean, there's some extent to that, but not really. But they wouldn't be. They would have the same amount of energy, but they wouldn't be moving the same speed. But they'd have the same amount of energy. Okay, that's an important difference to realize. Okay, I mean that's the science behind a helmet, right? The science behind a helmet is that when you get hit in the head, there's a certain amount of energy, and it's going to do a certain amount of work. Okay, but if I can make that work act over a greater mass, it's not so much about surface area, it's about a greater mass, then the amount of speed change will be decreased, right? So if I'm not wearing a helmet and I get hit in the head with a puck, okay, the puck only acts on like really that part of the head directly. If I'm wearing a helmet, then that impact is spread out over the mass of my entire head, right? So the velocity change by my entire head is less than the velocity change would have been to that one spot, right? That would probably break my skull. Whereas when I'm wearing the helmet, it's going to move my head to the side, right? I might still get a concussion, but not as bad as having a skull fracture, right, in that one spot, right? So it's not so much about surface area, it's about involving more mass. Does that sort of make sense? Okay, so mass is important when it comes to work and energy. Okay, it's really, really important because the more mass you have, the more work will have to be done to stop you, or the more work will have to be done to get you going. Okay, this is why I like to drive a truck. Because in an accident, there's a winner and a loser. Make no mistake. If you've ever been in a car accident or seen one, there's always a winner and a loser. Okay, the winner almost always is the heavier vehicle. Think about it. You're in a smart car and you hit a semi-truck. Okay? The semi-truck is going to win, hands down, unless the smart car is moving at, let's say Mach 3. Okay? The person in the smart car is still not going to survive, okay? But it might have enough energy to do significant damage to the truck if it's moving that fast. Not that a smart car can move that fast, okay? But the idea here is that the more mass you have, the more work you can do, okay? And I've been in a few car accidents. I would like to also point out that they were not my fault, okay? But, okay, being a physics guy, knowing kind of that stuff, being in one reinforces the importance of mass, okay? In fact, I always tell my physics kids, the most important safety feature in your car is mass. Yes, I'm not saying don't wear your seatbelt. I'm not saying airbags aren't important. Mass matters, okay? I once had an accident where a lady turned left in front of me. How she never saw me coming, I still do not understand, okay? But she turned left right in front of me, okay? And I was in my truck. And I went through that little car like a hot knife through butter, okay? Because I simply had more mass, okay? Her velocity went from being forward to backward, considerably backward, okay? Whereas mine continued to be forward, okay? That means good for me, bad for her, right? Because I had more mass, more energy as a result. I was also moving faster, but I was also the more massive of the two objects in the collision, okay? So as a result, my velocity changed less than hers. My velocity changed so little, in fact, that my airbags didn't even go off, okay? You have to have a certain amount of acceleration to activate the sensor that deploys your airbags, okay? My acceleration was not sufficient to deploy the airbags, whereas all of hers went off, okay? And the engine compartment, okay, I had intruded far enough into the engine compartment that I had snapped the engine mount bolts off, and the engine was just there, like kind of on the ground, okay, for her. I had to get my headlight assembly and front bumper replaced. Okay, mass matters, okay? She was okay. She was, shooken up for sure, but she was okay, okay? And yeah, it was, but all the airbags go off and all that kind of stuff. Mass matters because mass is part of all energy formulas, okay? It makes a big difference. Well, see, you can always avoid getting hit by a train. Yeah. How do they come up with these formulas? Well, a lot of experimentation hundreds of years ago. Mostly Joule, a guy named Joule. He did most of the stuff, and he was in that thing that you guys did that day I wasn't here, right? Talked about Joule and his experiment with the falling blocks, right? Converting potential energy. He showed that potential energy was a form of mechanical energy because when he hit the two blocks together, the temperature of the blocks went up. Okay, it's in there, but yeah. Basically, we know from measuring the speed of falling objects when they're near the ground that how much energy they must have had when they were higher up. And we know that these two are related, right? Okay, so this is mass in kilograms. G is the acceleration due to gravity, 9.81. Okay, that's on your formula sheet as well. H is height in meters. All right, and then in this one here, M is still mass. V is speed in meters per second. Yes, speed is squared in that formula, and we'll get to the effect that has in a few minutes as well. Okay, so for a force to transfer energy to an object, the force has to make the object move. Otherwise, D is 0, and we don't have any work. Andrew.
Like back to the energy, how much like energy would it take the speed of light?
Well, that's actually more this. Okay, C is the speed of light. M is mass. As this number, because it's squared, basically and this is going to be a really layman's way to explain this, but basically the amount of energy required to get something to the speed of light becomes nearly infinite, just because it's so fast, right? We're talking about such a major change in velocity. Okay, so it would be really an unfathomable amount of energy. I mean, remember when we did that question, that acceleration question, where we got the little proton, right, accelerated, and it took 86 hours or something like that to accelerate it, and it wasn't even at the speed of light? That was a proton, right? Now imagine trying to accelerate something big. Yeah, to physically, like in a Newtonian way, accelerate something to the speed of light would require nearly infinite amounts of energy. Basically, any idea of faster than light travel would have to involve some sort of dimensional skip or warp or something like that. And there's a lot of science that's showing that those ideas are not as far-fetched as we once thought they are. But again, the technology is not there, right? No. Well, yes. Would you survive it? No. Yeah, if you were sucked into a black hole, right? Yeah, then you could. No, terminal velocity is only something to do with falling through the Earth's atmosphere. In space, there's no terminal velocity in space. Theoretically, is the speed of light. Theoretically, nothing can go faster than that. Theoretically, right? Does that sort of make sense? Terminal velocity only has to do with air resistance equaling gravity. Yeah. Okay, so if we're looking at this situation here, okay, let's say in the first situation, okay, the golfer in both situations just swings normally. He can exert a certain amount of force with that swing. Okay, in the first swing, he's hitting a very small mass. That will produce a very large acceleration. Okay, in this, he's using the same force on a very large mass, which will produce a very small acceleration. This is why mass matters. Okay, in a collision, this is why mass matters. Right? The smaller mass is going to experience a larger acceleration. A larger acceleration means a bigger change in velocity. That means more force. That means bad for you. Okay? You want to experience less force, less change in velocity. You'll have less work done on you then, and you'll survive. Okay? Exactly. That's why linemen in football are not 120-pound skinny guys. Right? Linemen are 300-pound huge guys, right? Because you don't want them to move. Okay? Yeah. Okay, now, if from an energy perspective, when he hits his truck, is the truck going to move? Then is he doing any work? Yes, he is. Okay, will there be a dent in the truck? Okay, does that count as work? All right, if I'm standing over here and I have my hand on the front of the truck, will I know when he hits the truck? Well, not only will I hear it, but if I have my hand on the truck, I'll feel it, which means he moves every single particle in that truck. Doesn't mean he gets the truck as a unit to move, but he makes all the matter in the truck move. Okay, so he changes the kinetic energy of every single particle that makes up that truck, because that vibration is passed through the truck to the front, and I'd be able to feel it. Okay, so he's still doing work, just not making the truck as a unit move. Now, if he was out in space, or this truck was sitting on a perfectly frictionless sheet of ice in neutral, well, actually, it wouldn't even matter if it was in neutral. If it was a perfectly frictionless sheet of ice, and he hit it, the truck would slide. Not very fast, but it would slide. Okay?
What happens in a frictionless object? Say frictionful object. Is there going to be friction there, or is it like doing stuff?
So you're saying something with friction is sliding on a frictionless. That's not. The friction is gauged by the interface between the two objects. So there has to be no friction between them. It's not that one has it and one doesn't. Yeah, if you're on a frictionless surface, there's no friction.
Like, say there was like a big like metal object or something, I don't know, like, and you hit it. How would you not be like insanely tired after if you're moving every?
You do. If I keep hitting it, right? If I keep hitting it, I'm going to get insanely tired, even though I'm not really doing anything to the object, right? Every time I hit it, yeah, there's a big clang. So there's some sound. That's energy. Where did that energy come from? Me.
Like, if it's bigger, like, say it's like you're hitting a ball and it's like this big, and then one that's like really shallow, and one that's like really, really long. With one that's really long, like you'd get tired faster.
No, it's only about mass.
So you're not moving so harder.
Bigger the object. It doesn't matter how big the object.
Doesn't matter how big the object is. It just matters its mass. So it's like a ton of feathers and a ton of bricks. Okay? It's a ton either way, right? Yeah.
Okay, wait. So this guy's standing on a ledge and he's sitting in the truck. And you
Uh-huh.
said, like, imagine it was friction with ice or whatever.
Where the truck is, not where he is.
Right, but if he was also on the ice, wouldn't he, when he swung back, start sliding backwards?
Yep, absolutely.
Okay. So it doesn't matter which direction it's in.
Nope.
Any energy on a totally frictionless.
That's right. If you're on skates, right, and you have two people on skates, and if only one of them pushes, they both move. Right? That's that situation there. Yeah? Okay. So motion doesn't just mean the movement of an object from one place to another. Okay? When an object is compressed or stretched, its shape is changed, and that can involve potential energy in an elastic form. Okay? So when you're using a bow and arrow, okay, you can put potential energy into the bow and arrow because you're changing the bow's shape, and it's elastic and it wants to spring back to its original shape. Okay, same with a spring. If I compress the spring, I exert a force through whatever distance I shorten the spring. Okay, if I stretch the spring, same thing. Okay, I exert a force over whichever distance I made the spring longer. Right, it now has elastic potential energy. If I let it go, it's going to do work, because it wants to go back to its original shape. Okay, so a bow and arrow and a spring are examples that come up all the time because they're very easy to do. Force times distance equals a change in energy, which are work energy theorem type problems. Okay, so I could calculate, for example, how fast an arrow, as long as I knew the arrow's mass, could be shot from a bow, provided I knew how much force I used and how far back I drew the bow. Okay? If I knew those two numbers and the mass of the arrow, I'd be able to figure out how fast the arrow would come off the bow at. Okay? Because the work I would do, once I let go of the bow will do work on the arrow, and the arrow will gain speed and, as a result, kinetic energy. Okay?
Something is accelerating if they use like joules per second, something like that. Like,
No, energy we look at from a instantaneous perspective. We don't look at its changing over the course of, right? Like we say it's this and then it's this. The total change over that time is this many joules. Okay, joules per second is power. Okay, how much work I can do in a set time interval is how powerful I am, right? Okay, so work and heat are both transfers of energy. Okay, and you talked about heat kind of the first day. Heat is a transfer of thermal energy. Work is a transfer of mechanical energy. That is either potential or kinetic or both. All right, so they're similar in that they're both transfers of energy, but they're transferring different kinds of energy.
There's a change if so you said like D, right? And on the previous slide you would
Oh, DE.
there's a change in energy. What is that?
Oh, a delta E.
Yeah, so
Yeah, that's delta. Sorry. Yeah.
the change in energy with respect to what?
Final and initial. So let's say I'm talking about the bow and arrow. So we'll go back to this. Let's say I'm talking about the bow and arrow. Okay, when the arrow is in the bow, okay, it has no kinetic energy, right? Well, actually, the arrow. Whoops, sorry, I can't be F on both sides. The arrow doesn't have any energy. All the energy is in the bow. Okay, so if I've got an arrow in the bow and the bow is drawn, okay, the arrow has no energy of any kind. Well, I mean, I guess it would have gravitational potential because it could fall, but let's ignore that for now. Okay, so it's in the bow. The bow has potential energy. When I release the string, then the bow snaps, right? And it does work. It exerts, the string exerts a force on the arrow over whatever distance I drew it back. So all the energy I put into the arrow now gets transferred to the, or sorry, into the bow, gets transferred into the arrow when I release the bow. With me there? So the initial energy of the arrow is 0 because it wasn't moving, right? When it was sitting in the bow, its velocity was 0. So I could calculate, if I know how much force I used to draw the bow and how far back I draw the bow, I could calculate how fast the arrow is moving when it leaves the bow. Okay, does that sort of make sense? That's exactly the kind of thing we're going to work on. Right? Conversely, if I had that thing aimed straight up in the air instead, for whatever reason, okay, if I had the bow aimed straight up in the air, I'd be able to say the work I did in drawing back the bow could help me calculate how high the arrow would go, right? Because this would be mghf minus mghi, and I would just say that, well, at the beginning, I'm on the ground, and I don't have any potential energy. I could calculate how high the arrow would go. Again, we're only dealing with perfect physical world situations because it becomes very complex to start factoring in how much energy is lost against this, to that, whatever. So we don't. We just assume everything is perfect and all work gets transferred. It's inaccurate, but it's the way we have to do it for now. Nope. No, we're assuming everything is perfect. Yeah, the labs we're going to do, I mean, the sources of error will be a little bit more obvious than that. We're not going, when we do a lab, we're not going to assume it's all perfect. Okay, we're going to know it's not going to be. But I'm saying when we do problem solving, we're going to assume everything is perfect. Because if I have the arrow, if like I'm assuming I'm on the ground, right? So the amount of potential energy the arrow has here is negligible. It does have some, but it's not what we're figuring out. I just want to figure out how fast it leaves the bow at. Its height isn't changing across that distance. Does that make sense? Right? From when it's here in the bow and it's leaving the bow, its height doesn't change. So there's no change of potential. Okay. In the truest sense, this force times distance formula should look like this. Force times distance is the change in mechanical energy, which means the final potential plus the final kinetic minus the initial potential plus the initial kinetic. We just don't do both in Science 10. We make it, it's either a change in kinetic or a change in potential, just to simplify. Physics 20, first day, we do energy, it's both. Right? It doesn't make it any, I don't think it makes it a lot harder. You just have to keep track of two kinds. Okay, I'm going to get to that. I'm not there yet. Yeah. Okay. Yeah. Okay. We'll skip that part. All right. So for potential energy, okay, that's energy due to position or condition. All right. There's different kinds of potential energy. There's chemical potential energy. Gasoline and dynamite have chemical potential energy. There's energy stored in the bonds of those chemicals. When they react with something, the bonds break and the energy is released, usually as heat. Okay. There's elastic potential energy, which is the energy stored in any object whose shape can be changed, but wants to return back to, or has the ability to return back to its original shape. And then there's gravitational potential energy, which is possessed by any object above ground level. We are only going to deal with, mathematically anyway, gravitational potential energy in Science 10. All right, so Wile E. Coyote uses gravitational potential energy all the time to try and catch the Roadrunner. He also occasionally uses elastic, right? Because he almost always breaks, he breaks down to either trying to drop a rock up from a cliff on the Roadrunner, or he has some sort of like elastic band that's going to make him run faster or whatever, right? It's all, one form of energy to another. He's got to run, he can't run fast enough to catch the Roadrunner, so he has, rocket powered skates or whatever, okay? Things like that. So he's trying to convert those from that. All right, so with gravitational potential energy, which of those two people, those two blocks, are the same mass? They're identical. Okay. We're also going to assume that the plane, the ramp there that the girl is using, is frictionless. Okay. In putting their blocks to the top of that ramp, who does more work?
The guy lifting it has to put all of his energy from his body into the rock, whereas she can just slide it up.
But gravity's working on the friction.
Gravity's working on him too.
Actually, it's the same. They do the same amount of work. Here's why. Okay? Work is force times distance. It's also the change in energy. When these two blocks get to the top of this thing, do they have the same amount of potential energy? Yes, because they have the same mass, they're acted on by gravity, and they're the same height above ground level when they're at the top of the ramp. Regardless of how they get there, requires the same amount of work because I'm changing their energy by the same amount to get them there. Now, from a force times distance perspective, this distance is shorter than that one. Who has to exert more force? No, the guy. The whole purpose of a ramp is to use less force. Okay? He has to lift the rock, all of it. The ramp supports the rock. So she doesn't have to lift it, she just has to push it. So she uses less force over a greater distance. He uses more force over a shorter distance. Okay? The whole idea of a ramp, guys, is this. Okay? This guy here, gravity acts directly downwards on the rock. So he has to push directly upwards with the same amount of force as gravity. On the ramp, however, gravity wants to pull straight down, but the ramp prevents that, and it pushes back this way. So some of the force that she would have had to use to lift it is being supported by the ramp, which means she only has to exert this much force to push it up the ramp, which is way less than this. But she exerts it over the entire length of the ramp, which is longer than this. Okay? The whole purpose of the ramp, or the inclined plane, is what a ramp is, okay, is not to do less work, because that's impossible. It's to make work easier. All right? I can do the same amount of work using less force. Okay? That's the whole idea behind simple machines, to do the same amount of work using less force. Okay? So, I mean, this is how the pyramids were built. Make no mistake, aliens didn't help. Okay? Okay? The Egyptians built the pyramids by using thousands of slaves and sand. Okay? Can you make a really long ramp if you have lots of sand? Okay? If you have a really long ramp, you only need a few thousand slaves to push the rocks up the ramp. Okay? You need several 100 million of them that are all very brave to lift one. Okay? Because those rocks are huge. Okay? If you've ever seen the rocks, the bricks that the pyramids are made out of, you're not lifting those. Okay? They would pry them up and get logs underneath them. Okay? And then they would roll them, and the log would get to the back. They'd pick it up, move it to the front, and keep going.
If the guy were to drop the rock and slide it down the ramp and hit the girl's rock, would the girl fall, or would the rock just hit each other?
It would depend how fast she's going, whether she can continue to hold on to the rock. There's a whole bunch of things that could possibly happen there. Maybe the rocks shatter. Like, it's hard to tell. Yeah. Yeah, I'm just saying. Yeah, I know she would have trouble walking up the ramp if it was frictionless. Okay, let's say that she was using a pulley system to pull it up the ramp, and the ramp was frictionless. Is that better? Yeah.
So let's say like in space, there's like still planets around like gravity, whatever. And it's like there's two, like the same way that like in perfect squares, like both. If they collide head on, do they bounce back?
Yes. Well, it would depend if they're moving at the same speed. Yeah, then they would just hit each other, and that'd be it. Yeah, because their energies and momentums would cancel. Right. Now, again, that's if they don't change shape at all. Right. In the real physical world, right? I mean, one of them could be stronger than the other. I mean, if they were absolutely perfectly identical and their shape couldn't change at all, then they would just stick. All right, so gravitational potential energy is the potential energy of an object due to its position, okay? So all forms of potential energy are described with respect to a chosen reference point or condition, okay? Reference point, usually ground level, right? But a question could say, what's the work done in going from the second floor of a building to the fourth floor of a building? In which case your reference point isn't the ground, now it's the second floor, okay? So you kind of just have to watch for that, okay? In a case like that, you'd have work equals the change in potential energy. So you'd go m times g times hf, that would be the height on the fourth floor, minus m times g times hi, I keep writing f twice, hi, okay, that would be the height on the second floor. Okay, you'd still calculate the work done there. No, because it's being subtracted, right? You don't cancel things when you're subtracting, only if you're dividing. Yeah, you could do this. You could go that would also work, right? The change in height. It works for this formula. It won't work for kinetic energy because it's squared in the kinetic energy formula. mgh. Okay, this is the final potential. This is the initial potential. Yeah. So mass times gravity times height gives you the potential energy of an object. Right? The more massive it is, the more potential energy it has. Again, what would you rather get hit by, right? Something small from the second floor or something big from the second floor? Something small, right? Okay, so we can calculate the gravitational potential and the energy of the object using this formula here. Mass times the acceleration due to gravity, which unless you're told otherwise is 9.81 meters per second squared, because we're going to assume that this is all happening on Earth, unless a question specifically states it's somewhere else, or that the acceleration due to gravity is some other value for whatever reason. Okay, and then h is the object's height above the ground or reference point in meters. Right. So when we do this, okay, we're going to have kilograms multiplied by meters per second squared multiplied by meters. Okay, this is our mass, m times g times h. What am I going to get for units? No, the m's won't cancel. They're both on top. What's meters times meters? Meters squared. Okay, so I got kilograms times meters squared per second squared. So in other words, I have a kilogram meters squared per second squared. That's a joule. You can just write it as joule. Is that okay? I don't think the actual units are on your formula sheet. Okay, but a joule is a kilogram meters squared per second squared. Aren't you glad for joule? Yeah. Okay. No, because they're not. This is seconds squared. This is meters squared. I can't cancel. That's like saying apples squared cancels oranges squared. Right? They're different. Not that you could have a square apple. Well, you could. You could grow it in a box. Now we're just digressing. Okay, so does that formula make sense there, guys? See? So the units are joules. Now, if we're looking at kinetic energy, remember kinetic energy's formula was 1/2 mv squared. Am I still going to get joules? Yes. Okay, because mass is in kilograms and speed is in meters per second, but it's squared. Kilogram meters squared per second squared. Still get joules. Okay. All right. Okay, so first example here. Okay, we got a 3 kilogram box lifted by an upward force 1.5 meters above the surface of the Earth to the top of a table. What is its potential energy in its new position? All right, well, potential energy is mass times gravity times height. So I take my mass, 3 kilograms, multiply by 9.81, multiply by 1.5 meters, and I get that its new energy is 44.1 joules. Okay, so it could do 44.1 joules of work from that point. Everybody all right with that? Yep, that's all it could do. No, you would have to be able. You would have to drop it. Yes, you would have to drop it. Yep. Okay, that fairly straightforward. How easy is this formula going to be to manipulate? Pretty easy because everything is what? It's all multiplied and it's all attached. So if I want to isolate something, what do I do with the other two things? Divide them to the other side, right? It's an easy formula to use. Okay, easy manipulation. Okay, so example where we have to manipulate it. I have a 55 kilogram diver standing on a platform, and they have a gravitational potential energy of, that should be times 10 to the 3. Okay, so 5.4 times 10 to the 3 joules. What's the vertical height of the platform? All right, so we know that EP is m times g times h, but now we're looking for the height of the platform. So as we said, we would divide both sides by mg. That'll leave us with h. Everybody okay with that? Okay, so when we plug in our numbers, we're going to have 5,400 joules, okay, divided by, and then this would have to be enclosed in brackets on your calculator. So it would have to look like this. Okay, so we'd have 5,400, okay, divided by 55 times 9.81. Okay, so it's 10.8 meters. Everybody all right with that? Okay, so that's a pretty high diving platform, right? Why did I get 10.8? Did I type something in wrong? Oh, because I put 9.1. Okay. I don't need to square it. No, the units are meters per second squared. The 9.81 isn't squared, right? That's better, 10 meters. So it's the 10 meter diving platform, right? That's the tall one. Okay, questions on how that works? Okay, that formula fairly straightforward? Okay. All right, so I'm going to show you here, guys, just a couple of examples of using kinetic energy to do work. Okay, I'm going to show you the guy who currently holds the world record for breaking sidewalk blocks with his bare hands. All right, it's like 27 or 28 sidewalk blocks stacked. Okay, now in order to pull that off, obviously you have to have practiced a lot. Okay, but you also have to have the right technique. Okay, can you just stack them right on top of each other, or does there have to be a space between them? There has to be a space. Otherwise, you're breaking one really thick piece of concrete, and no one's going to do that. Okay, so they have a little space in between them because you have to be able to move through from one to the other. Even breaking one is impressive, right? Yes, but all in very quick succession because they are all stacked. There's other guys who have the speed records, and they have like all these bricks, and they just, right, and they just walked. Like there was one guy, he walked for like a block and a half breaking these things, and he broke his hand, and then he kept switched to the other hand, and he was like, yeah. Okay, Paige, can I get you to turn that off for me? All right, so a little bit of backstory here. This guy is an American Army veteran. He was blinded by anti-infantry device, okay, in Iraq, so he can't see. He's totally blind, but he's still able to do this. That's why you see two people leading him up to the stack of bricks, and then he kind of feels them out to figure out where everything is. His son is on the camera. So he's using his elbow. Okay. So, I mean, the key to that obviously is there does have to be that space there, because once you break the first one, okay, you have to be able to continue to exert that force through to the others. Now, do you start getting some help once you've broken a few? Because what are you adding? Mass, right? You're adding the mass of the bricks above. So if you continue to push on them, it's not just the mass of your arm. You've got the mass of the other bricks you've broken pushing on the others, okay? But there does have to be a space of a certain amount between there to allow the brick to break and for your force to be transferred down to the next one. If there's no space, you have to break the whole thing with one shot, okay? And nobody's going to do that. So that's converting kinetic energy, okay, or using kinetic energy to do work, changing the shape of the bricks, okay? There's all kinds of other examples of kinetic energy as well, okay? Moving molecules in a sound wave, make your eardrums vibrate back and forth. That's how we hear. If you have too much sound energy, what can happen to your eardrum? It can shatter, right? It can tear, perforate, okay? That's very bad because there's little bones behind it, okay? So tomorrow, listen here, guys. Tomorrow, okay, Mr. Eden will be back and he's going to play the kind of second half of this lesson, and then you'll probably get going on some questions from the worksheet depending on how well things go, all right? Monday, I'll be back. We'll work on this some more, and then Tuesday, I'm looking at doing a lab on work and energy, okay? Watch the podcast. Yeah, I'll post them in Google Classroom, same as I always do. Yes. Yeah. I was going to have one today, but my son's surgery got bumped, and then, yeah. Paige, can I have you turn that light back on for me, please? Thank you.